In this video, I'm going to introduce differential calculus to you. Now, I'm sure you've been hearing for many, many years of your life that calculus is quite the killer in math, but I'm here today to kind of get you used to the idea that calculus is not so bad. So what is calculus? Well, that's a much bigger question than I'm willing to answer today, but we're going to start looking at differential calculus and what that means and what we can connect it to. So let's take a step back for a moment and think about when we learned about graphs that would have, let's say, time on the x-axis and distance on the y-axis. And then we learned that a car, as time went on, the distance would change. And then perhaps somebody told you that, well, if you found the slope of this line by doing simply rise over run, then you'd be getting distance over time, and that would give you something special. Now, if you remember well from, maybe grade 7 physics or something like that, you'll remember that that would give you speed. So you can actually graph somebody traveling along. So this is my car and it's traveling along this straight, perfect line. And as time passes, the distance is changing, and that way you find the slope that gives you speed. Now, here's the thing. In the real world, no one ever starts running or driving at the one speed and keeps going at that speed. What's more likely to happen is this. You're in a car and you start slowly and then you speed up. So as time, that's super fast, but as time changes, the distance is still changing, but in the real world, the distance isn't changing uniformly. The distance is changing at a different rate every time you look at this vehicle or this person. He's accelerating, he's going faster and faster. And then maybe he might slow down at some point and then stop. All right, so that's really what happens in the real world. But we want to be able to figure out slope at any point in time. So if I wanted to figure out the slope here, I could look at a line that goes here, or if I wanted to look at the slope here, but this is very complicated to try and figure out exactly what the slope is at teeny tiny points on a graph. So instead of having to see the slope, draw a line, which we'll talk about that line in another video and what that's called, but instead of having to look specifically at that line at that point, so right here, the slope would be here, there is something that we can do in order to figure out the slope of any graph once we have an equation for that graph. So what's that called? What's the process of finding the slope of any point on a graph, even if it's curved? Well, that process is called differentiation. So let's look at that for a second. Let's go over what we just spoke about. So differentiation is the process that gives us the expression for slope anywhere on any graph, as long as you have the equation for that graph. So again, if I had a graph that looked like this, for example, that looked like this, and we had the graph here, if I differentiate, we can find the slope anywhere on the graph. We could find the slope here, 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 anywhere on this graph we can find the slope. So what does this process entail? Well, it's a two-step process for the simple ones, and we'll just look at a simple differentiation example for now. So let's use, for our example, let's use the graph of y equals x squared, because most of us are aware of what that graph looks like. And if you're not sure of what that graph looks like, of course, feel free to type that equation into your TI-84 or whatever graphing calculator you're using. I'm doing a very bad job here, but it should be a parabola with its vertex at 0, 0. And of course, it keeps going that way. All right, so my argument is this. We can find the slope of this graph anywhere on the graph. As you can see, the slope is positive on that side. It's negative on that side. And it's constantly changing as you're moving through the graph. So how do we find the slope? Well, we have to differentiate or find the derivative. All of these things are the same thing. All right. There is a two-step process for that. So step one, we need to multiply the exponent by the coefficient. And we'll talk about what each of these things are, just in case you're not sure. And that will give us the new coefficient. All right. So what's an exponent? What's a coefficient? Let's briefly speak about that. The power, that's the exponent. So we have an exponent of 2, and the number that comes before the x, that's the coefficient. In this case, we don't have a coefficient that we can see, which means that our coefficient is actually 1. So when we multiply our exponent 2 by our coefficient 1, we get 2, which is our new coefficient. So let's just make a note of that right there. Step 2 is to subtract 1 from the exponent to get the new exponent. So subtract 1 from the new exponent, from the exponent to get the new exponent. All right, so our exponent, or original exponent, is 2, as you may recall. We need to subtract 1, and it's always 1. Subtract 1 from that exponent to get the new exponent. So our new exponent is 2 minus 1. So our new exponent is 1. So our new coefficient is 2, and our new exponent is 1. And our derivative, or the differentiated or slope, the differentiated equation or the slope of our original graph is 2, because that's the new coefficient, x to the 1. And of course, we don't have to write to the 1 because it's assumed. So that will tell you the slope anywhere on this graph. Now, the notation used to write the derivative or the differentiated equation is dy over dx. Now, this is not telling you you have to divide anything by anything else. It's just notation to say the differentiated equation is. So it's a shortcut of saying our differentiated equation is. So instead of saying all of that, we can just say dy over dx equals. Let's try another one. Okay, so my equation here is that y is equal to 2x to the third. And if you graph that in your calculator, and I'm not a very good sketcher here, but I will do my best. If you graph that in your calculator, it looks a little something like that. A little something like that. Not perfect, but that's the idea. All right, so now in order to figure out the slope anywhere on this graph, we would have to differentiate. So when we differentiate, so again, remember our notation says dy over dx. That's just saying when we differentiate, what we get is. So remember, to get the new coefficient, we need to multiply our exponent by our coefficient to get the new coefficient. So 2 times 3 gives you your new coefficient, which is 6. We still have x here. And to get the new exponent, we have to subtract 1 from the old exponent. So 3 minus 1 will give you the new exponent. So our new exponent is 2. So this will tell you your slope anywhere on this graph. Let's see if it makes sense. Right here, Looks like a little bit of a point of inflection, which you don't know what that is yet. But it looks like the graph is flattening out for a second, right? So if the graph is flattening out for a second, I'll redraw it here so you can see it clearer. It's flat here. It's like you're walking up a hill for a while and then you get a little break and then you go back up a hill. So right there, at that point, the slope or the gradient is 0. Let's see if it makes sense according to what we have here. Well, what is x at that point? As you can see, since it's the origin, x is 0. We don't care much about what y is, but y is also 0. All right, so x is 0, which means that this, which tells you the slope, or slope, is equal to 6 times 0, because remember, x is 0 squared. So our slope is equal to 0. And that makes sense. And you can actually go ahead and find the slope anywhere on this graph, where x is 1, where x is 2, where x is negative 100. It doesn't matter. You can find the slope anywhere on this graph by differentiating. Now let's just look at one more example that's slightly different. Okay, so in this example, there are a few things that I want to really bring out. And the first and most important thing, well, they're both important. The first thing is the fact that we can find the derivative of multiple terms just like we did before. So our derivative, so when we differentiate, we get an answer of. So again, remember, we're multiplying that by that to get the new coefficient. So the new coefficient is 6. Let me use a different color here. The new coefficient is 6. X to the, and then again, we're subtracting 1 from our exponent. So we're subtracting 1 from 3 to get 6x squared. And then we can go again and do the same thing again, multiply our coefficient by our exponent to get our new coefficient, which is 4x. Subtract 1 from the 2 to get our new exponent, which is 1. Now things start looking a little bit different on this side, the right side of our equation. We don't have an exponent here. So if x is not raised to an exponent, then the exponent is 1. And our last term, there is no x at all. So it's actually just like saying x to the 0. So now we can go ahead and keep finding our derivatives, keep differentiating. So we have negative 1 times 1 times negative 5. That gives you negative 5x to the 0. And finally, the last one, plus 0x to the negative 1. But we have a bunch of stuff in here that is nonsensical. We don't need some of it. So for example, we don't need to have that one there. X to the 1 is just x. So if I'm covering it in red, it can go. So that's covered in red. We don't need that one. X to the 0, if you recall, anything raised to the power of 0 is 1. So x to the 0 is just 1. We don't actually need to have that written there. So that actually should just be 5, and I'll rewrite in a second. And we have 0 times x to the negative 1. Well, that's just 0, isn't it? So our derivative that we actually got was that 6x squared plus 4x minus 5. That was our answer. So what did I want you to actually take from this side of our equation? Well, 2 points. If you differentiate anything with an x and just an x, so for example, I'll make a little table over here. So for example, you have y is equal to something like 4x squared. If y is equal to 4x squared, y is equal to 4x. So if y is equal to 4x, then dy over dx, or derivative, or differential will be equal to just 4. It just goes away. So if y was 5x, our derivative would be 5. If y is 1,000,000x, our derivative would be 1,000,000. If y was negative 3,000x, our derivative would be negative 3,000. In a similar way, if y was 5, our derivative would be 0. Any number with no x, our derivative is always going to be 0. So if y is 700, our derivative is 0. If y is 9,000,000, our derivative is still 0. Because the slope of y equals a constant, the slope of y equals 5, for example, is flat. It's not going up at all. So the slope is always going to be 0 if we just have a number with no x.